Good morning everyone. Myself Raka Mandal. So today we are going to talk about membranes for fuel cell. So before proceeding, let us understand in a hydrogen energy where the fuel cell comes in picture. The fuel cell basically is a method or a mean to convert the hydrogen from its fuel form to our energy, useful energy. So basically we have the steps as like production of hydrogen, then the storage of hydrogen which we previously discussed, then we proceed to combustion of hydrogen where the hydrogen reacts with oxygen and produces energy for that. So role of fuel cell is that it provides you a source of clean energy because it does not generate any greenhouse gases, and it can support all levels of energy demand, like from transport where the energy demand is low to grid supply where the power demand is very high, and also in industrial application also. Now in this session we will be talking about how a fuel cell works, then the types of fuel cell, the comparison, the composite membranes, desirable properties of a composite membrane, challenges, the different manufacturing technologies, government policies and future research. Now before talking about fuel cell, we need to understand a basic thing is that in the very first lecture we talked about electrolyzer, generation of electricity. Their structure is also given up of anode, cathode and a polymer electrolyte mainly. Same also is the composition of fuel cell also, anode, cathode and polymer electrolyte, but the main difference here is that instead of having a power source which we have in electrolyzer, here we can generate power and use it for like lighting purpose or other purposes. So in a electrolyzer, the input to us for the cathode side is, the input is for the cathode side we have water as a input and we generate hydrogen at the cathode, we generate hydrogen, in the anode we put the input of water, and in the anode only we generate the oxygen. But in fuel cell the input and outputs are different. What we have is that hydrogen we give in the anode side. So this is typical to the PEM fuel cell. So if we have different kinds of fuel cell like MCFC or SOFC, there the inlet can be different. Like hydrogen it is given in the anode side and oxygen is given in the cathode side. So hydrogen goes to this catalyst layer and generates into H+. It is transported through the polymer electrolyte or the membrane towards the cathode. Then they react with the electron and generate the water molecules through it. So water molecules and is generated and the power is generated. So we do not see any CO2. We have a composition of hydrogen, but no CO2 production, no greenhouse gas production here. Now our difference between electrolyzer and fuel cell is clear. Now let us see, in a fuel cell also we have different types very similar to that kind of a electrolyzer. So like in PEM fuel cell we have a polymer electrolyte which is sandwiched between the anode and cathode, and it is most efficiently used in the temperature range of 60 to 80 degrees centigrade. The generation of power is in a such a way that it is very useful for transport sector. Okay. The SOFC is more of a preferable choice when we go to SOFC. In a SOFC the ion that is conducted is O2 minus. Okay. It is more commonly used in industries. So the operating temperature is very high also, 500 to 1000 degrees centigrade. So for power grid application or industrial application, this SOFC is more useful. We also have a counterpart of PEM fuel cell, that is alkaline fuel cell. Most of the fuel cells that are currently in use as a commercial scales are alkaline fuel cell, where we have alkali, simple aqueous solution of KOH or similar to that, which is used as a electrolyte in this case. But here what we see is that if we have this kind of liquid electrolyte, then there are a lot of chances of poisoning of the electrode material. So, in order to recover that, what we do? We apply a membrane in place of a electrolyte, in place of a liquid electrolyte. We use a membrane. In that case, it transfers to alkaline membrane fuel cell. Okay. So, we do not have any liquid, we only have a solid membrane in that case. So, this AFC also operates at a moderate temperature like 50 to 200 degrees centigrade. We also have phosphoric acid fuel cell or PAFC, where we have the electrolyte is mainly dipped into phosphoric acid. So, they also operate in around 150 to 200 degrees centigrade. MCFC is in turn another option. PAFC is a very good choice for moderately heavy vehicle like submarine, etc. And molten carbonate fuel cell or MCFC, they have also lithium carbonate or completely inorganic membrane as a part of a electrolyte material or membrane. So, that is used at a very high temperature 600 to 700 degrees centigrade. Now, these membranes, their main purpose, as we have been telling that in a fuel cell, their main purpose is to stop the intermixing of anode and cathode gas, but at the same time transport the ions separately. So, they have a very huge role. They especially in fuel cells like PEM and etc., we see that the cost of membrane is comparatively lower than that of electrode material. But it can often be a rate limiting step. If the transport through these membranes are very slow, then they can be a rate limiting step and they can reduce the efficiency of a fuel cell. So, that is why it is told that in a fuel cell the membranes or the electrolytes are the heart of a fuel cell. So, it is very useful to or very important to have them in a very good condition. Now, let us look at the efficiency level. PEM has an efficiency of around 50 to 60 degrees centigrade. So, as a rule basically that is that whenever we require very high temperature like more than 500 degrees centigrade, we have to ramp up the temperature, and in order to ramp up the temperature we need certain time to reach that temperature level. So, that is why it requires a little time to start fuel cells like MCFC, SOFC, etc. So, just the initial starting time is quite considerably high. That is why they cannot be used like in a automobile industries. Imagine that you are using a MCFC in your car and you are waiting for 1 hour before your car starts in the college or the office. So, you will always be late. So, you do not want that. Okay? So, that is why we have to have a very quick starting of our fuel cells. So, that is why PEM or AEM are more, they find their application more in the mobile side of our of our application. Okay. So, that is why they are very useful choice for space, military application. They vehicle for that they are alkaline and PEM fuel cells, they are more useful. We have a methanol fuel cell also. In methanol fuel cell, we have methanol as a fuel. Okay. Otherwise, mostly they also use polymer membrane and very similar to PEM. Okay. Their operational efficiency lies around up to 50%. So, they have a small power off grid power like domestic power uses, etc. They can be used for this kind of application. But phosphoric acid fuel cell is for plant operation, is or for heavy duty vehicle, and for molten carbonate fuel cell, as I was telling that their efficiency is around up to 60%, but they need a carbonate mixture as a electrolyte or membrane material. Now, it has been, yesterday probably I was telling you about this Toyota Mirai car. They have been cited as one of the benchmark of automobile industries, because they have given a very good, they have used a fuel cell for generation of power, hydrogen fuel cell of a PM category, but they have shown that 5.4 kilowatt per liter in the current generation of their car, they can use this kind of power generation efficiency. So this is till date the highest for the power generation efficiency. Okay. Now that we know a little bit about the different types of fuel cells, different how they work, what is their efficiency or application. Now let us look a little bit more into those specific type of fuel cell where we need different kinds of particular membranes. Like in PM membrane, how do they look? This image basically is showing you assembly of a fuel cell. Okay. So in a fuel cell, the different MEA or membrane electrode assembly, they are stacked and sandwiched between two current correction like this. Okay. So in a MEA, if we look or if we broaden the MEA structure, we will see that at the center of the MEA we have a membrane. On the two sides we have the anode and cathode. So we have a catalyst layer on the two sides of the membrane. We have frame to hold them, and there is also gas diffusion layer or GDL at the two sides of the membrane, so that this diffusion of gas or mass transport is efficient, they become efficient. So this is the construction of a MEA, and this is how internally a single cell looks like. Okay. So internally we have a mass transport to the GDL, and then we have reaction, diffusion, electromigration. We sometimes have drag also. What is drag? Drag is basically because of the water flow rate or because of the flow of ion charge, the opposing charges are dragged with them. So against the flow field, against the potential field, they are dragged with them. So they effectively reduces the efficiency of a fuel cell. So these are the some of the transport mechanism which works a lot, which features a lot into determining the efficiency of your system. In this type of membrane, we have power density around 1 watt per centimeter square. Their lifetime for in a stationary application is around 40,000 and 50,000. The key component of this MEA or the membrane is a Nafion membrane. So Nafion membrane or PTFE membrane, they are the most popular or the most commercial membranes in this kind of sector. Now they enable gain energy storage, and so these kind of things we have already discussed that they are mainly useful for good energy storage and application. Now let us discuss a little bit about basically how to assemble this MEA. Now that we know these compositions of our MEA, now we have to make it in such a way that our losses, the transport losses through them should be minimized. Now let us see one of the typical example, one of the typical case studies reported in a very highly cited paper. They have taken the membranes in such a way that they have some catalyst. Here they have, in this particular paper they used platinum carbon catalyst. They used some ionomer which they will be using for making a polymerization, and some solution. They made a they added a solvent and they mixed it very vigorously. Okay. Now the solution then they get, they call it ink. Ink is like the, while the printer we have the cartridge, in that the ink, so it is like that only, that they are calling it a ink, which is basically a mixture of these three components. Now then they pour it in a die, okay, a slot die. What is this slot die? Slot die is basically a big mechanical component where they have a very thin slit, okay, thin slit in between two metal plates. Okay. So now, and at the bottom of this metal plate they have a roller rolling. Okay. So now imagine that a polymer film, if we put into this thin slit and a roller is rolling, then there will be a constant continuous coating onto the roller surface. Now what they do is that they make a conveyor belt attached to this roller surface. Now what this conveyor belt will do? They will carry this film that is constantly being generated onto the surface of your roller. Okay. So now they are constantly generated. Now they with some arrangement of pulley system and conveyor belt, they do rolling of this. Okay. Rolling means that what? That another pulley or another roller is moving around in a opposite direction, and it's like a spindle. It wraps it around, wraps the MEA around it. Okay. Now after that, what they do? They put everything onto one above another, like this assembly of frame, GDL, then this is the CCM they are telling, that catalyst coating, and then they put it in the assembly, and then they do pressing, hot press. Okay. So pressing is not just manual pressing will not be sufficient, because whenever we just assemble them like this without creating any extra pressure, then there will be a lot of gap between these layers. Okay. There will be maybe not visible through eyes only, but there will be small gaps which will enhance your contact resistance. Contact resistance means that the generation of ions and then going from one layer to another layer, there will be a lot of extra resistance to that. So in order to recover that, what we generally do is that we make it in a hot press. So we create a lot of hydraulic pressure, we enhance a little bit of temperature, so that the contact between these layers, they are minimized. Okay. So contact is very good, and we have a very minimal or no gap at all between the layers. Okay. So this is how a MEA is produced. Now once the MEA is produced, the stacking is very easy to do, like you just have to put it one over another and make it sandwich between the two end plates. Okay. So that was about the fuel cell assembly or MEA assembly that can be done, or that is generally done in industries or in normal or for real life application. Now let us look a little bit in the AEM type. Okay. So in the main difference between the PM and AEM is what? That in PM the ion that we are transferring is H plus. Okay. In the AEM, the ion that we are transferring is OH minus, and also the ion direction of ion transfer is also the reverse. We have the direction from cathode to the anode side. Okay. Now they have a polymeric back, their structure is also a little bit different, so that they can conduct or transport hydroxide OH minus ions. There has to be some OH minus ions, so these membranes can be soaked in a KOH, so that they can be effectively having lot of residual OH minus charges. Okay. And the reaction in the anode side is they generate these, so let us talk about cathode side first. So in the cathode side, this oxygen and water, they take OH minus, and these OH minus makes up of another water. So this is the overall reaction that we have for our AEM fuel cell. Water is generated in this AEM fuel cell also. Other than that, other than the difference in the transport properties, the stacking for AEM is also similar that of PM. Okay. We have to have a membrane, we have to stack it, we can press it, print it. So like that, these are the same steps that we follow for AEM or fuel cell, AEM and PM, but the material of these components, they are different. Let us talk a little about phosphoric acid fuel cell. You know, phosphoric acid fuel cell, it got a very good application in heavy duty vehicle. So in the phosphoric acid fuel cell, basically what we have is that we have PBI membrane or silicon carbide membrane, which are held in phosphoric acid. So they are immersed in phosphoric acid. So that's why this name comes from phosphoric acid fuel cell. Okay. They are also, they transport H plus. Okay. So this fuel is basically again phosphoric acid that we are having, then mostly hydrogen also we can give it here, and hydrogen, the high proton it gives you higher proton conductivity than your PM membranes. Okay. So because it is again a inorganic membrane material having a lot of ions, so they have got a good power density, and durability is also very similar to that of previous one or PM one. Okay. So, they apart from the heavy duty vehicle, they can be used for stationary power generation or large scale power backup system. Like often in maybe not in India, it is not very popular till now, not widespread till now, but in abroad it is very common to have a power backup in hospitals or others in terms of PEAFC. Okay. So, that is like a last power sources, they are very reliable like that. Okay. So, now we have talked about these type of polymeric membranes. Let us talk a little bit about inorganic membranes. Okay. So, in earlier classes we talked about a lot of types of membranes that we use for hydrogen energy. We have seen that apart from polymeric membrane, we have inorganic, ceramic, these kind of membranes also. Now, in this type of particular fuel cell, molten carbonate fuel cell, what we have is that we have lithium carbonate and potassium carbonate, like basically metal carbonate. Metal carbonate is used as a electrolyte or a membrane material sandwiched between the anode and cathode. What they do is that you have to elevate the temperature up to over 700-800 degrees centigrade, so that they are in a molten form. That is why molten carbonate fuel cell, these electrolytes should be in a molten form. It is very important to make it in a molten form so that they can transport the carbonate ions. Now, this molten form is important because in a solid form their transport properties is not very efficient. That is why in this type of fuel cell the startup time is also very high, you have to ramp up the temperature. Okay. But one advantage they give is that they have very high power density, their efficiency might be lower, but what they give is that the amount of power generated is, it can be very high. So, that is why for power plants it is a very preferable choice. Okay. So, they will give lot of power, you can even make it in line with some carbon capture efficiency to make the process more economical, more sustainable. So, these are some of the MCFC features, but here keep in mind the membrane that we use, they are of metallic carbonate in nature and they have to be in a liquid form or molten form to make it work. SOFC or solid oxide fuel cell, they are very similar to molten carbonate fuel cell, only major difference is that the ion that they transport is O- oxygen ions, okay, O minus minus. So, the electrolyte is again a non-polymeric membrane. We have a yttria stabilized zirconia, YSZ, that is a most common material. Other than this doped ceria, basically the zirconia is a very popular choice for SOFC. Okay. Then we have oxygen transport through them and we have a very good power output. You might have noticed that this power output value is much higher than the previous ones. Okay. And they can have good durability also, transportation and defense, they got a very high power generation output like that. Okay. All right. Now that we have talked a little bit about the types of membranes for different types of fuel cell, let us see that I was telling you about loss of the fuel cell. Okay. So, what are the different types of loss that we can see in a fuel cell, or where the membrane comes in picture in this loss? Okay. So, this is what I am showing is a polarization curve of a typical fuel cell. So, this green line is basically giving you the reversible standard potential, which is determined by the thermodynamics of the operation. Okay. So, this is the maximum operation, that maximum efficiency that you can use for any type of fuel cell. So, now generally for fuel cells like PEM, AEM, they operate at a voltage value around 0.6 to 0.8 or 0.9 up to that much range volt. Okay. Now, if we see this is the IV curve, that means the voltage in terms of current density, this we see normal standardization curve for a fuel cell. So, this purple line, this purple line is actual VI curve for our system, okay. So including or considering the losses. So what are the losses? Reaction rate. Reaction rate is first, where is the reaction rate? Reaction rate is that where we are generating the proton, where we are generating the ions. There the reaction rate, for that this loss is dominated by the activation polarization or the generation of ions. This is the resistance to the transport through the membrane, okay. That is why this ohmic polarization, this is ohmic in nature, like V equal to IR, that that kind of formula it is following, that is why it is linear in nature. There are some concentration polarization or gas transport loss, it is basically the mass transport losses. First one is for reaction, the last one is for mass transport. The losses is basically for that. The middle one is for the ohmic transport. Now this is the total effective graph that we see for a real fuel cell, and any time the difference between this green line and the purple line, it is giving you the total loss. Now in this total loss, the cathode loss in the reaction rate loss, that is most of the time more dominated. In the membrane internal resistance loss, it is basically it is giving you the slope of this straight line. So if the slope is very high, that means that our membrane is giving you very high resistance to the transport, okay. And also if there is very high mass transport resistance, this drop also will be very sharp. So if your membrane is good, you can expect this slope of the straight line to be lesser, okay. I mean, it is a more flat line and less difference between these two. So this is one of the polarization, this is one of the aspect how we get or we determine how your MEA is working, okay. Now the next question that comes to our mind is that how to know how many stacks to put MEA. So generally in lab scale, when we are testing any membrane or we are testing any assembly, we generally go for 1 or 2 to test any new membrane like that, okay. Like 1 or 2 MEA, that I have shown you the picture of sandwiched MEA between the 2 end plates. So these MEAs or the film 1 or 2 is maximum that we go for lab scale. But in industrial scale or maybe even in automobile, the voltage output that you require might be higher, where the 1 or 2 MEA number of slides might not be sufficient. So in that case, each cell will generate some amount of voltage potential, and that is basically summed up to get you the effective total velocity. So like say that you need to run your car, you need 1.6 and your 1.6 voltage difference, and now each of your MEA is giving you 0.8. So total 8 number of 0.2, let us say. So total 8 number of MEA stacks you have to put all together to get it, okay. Now while stacking, what is stacking? Basically stacking means that one cell's cathode of one cell should be connected to the anode of the next cell. That is the main stacking material, okay, stacking method. So it should be uniformly distributed fuel and oxidant, temperature must be uniform, you should have if you are dealing with a polymer electrolyte, it is very important not to dry it out. There should be a proper management of water, which I will explain in more detail later. Stack might be must be sturdy enough so that there is no leakage. There should not be any mechanical failure during the process, okay. So these are some aspects when we have to take care of the stacking arrangement. So in this slide, basically I am showing you most of summary of what I have talked about the different kinds of fuel cells. So you can, if you have a look of these stacks of these materials, then you can easily have a summary or overview of a fuel cells that are. Now, as I was telling that, yes, so now it is important that how to get the material, what particular material we should choose for different kinds of application. Other than that, that the structure of the membrane is sometimes it becomes important for a particular application, like hydrophilic channels that I was explaining yesterday, that the polymeric backbones make the two boundaries of your hydrophilic channel. The side chains, they give you the functional hydrophilic space for the water to transport. So for that, the thin polymeric film is necessary for PEMFC, like that. But in phosphoric acid, why we need the phosphoric acid? Because in that one you need more phosphoric acid to transport them, like phosphoric acid acts as a vehicle for a phosphoric acid transport movement fuel cell. Okay. This MCFC porous ceramic matrix, they are also having molten carbonate, otherwise they cannot transport the electrons. And for ceramic cycles, for SOFC, they have to be very dense, otherwise what will be there is that they face a lot of losses, transport losses. Okay. Alkaline fuel cell, I already explained that you have to soak it with a saturated KOH, okay, so that they can transfer OH minus effectively. Okay. Now that we know about the types of membranes for different types of fuel cells, their particular application, their particular structure, their particular operating condition, let us see that how to improve these efficiencies, because you see that efficiency for mostly for membrane based fuel cell like PEM or FESEM for AEM, we face a lot of losses, like around 60% is the efficiency that we see. Now in order to improve that, many researchers all over the world, they are working on this composite membrane. So in a composite membrane, especially when we have a PEM type of membrane, we can have organic polymers blended with nanoparticles like silica or zirconia, like that. So basically what they are doing is that when we are seeing these water channels, when we go to a higher temperature or lower humidity, sometimes they collapse. Now if you have in between these hydro channels, if you have some nanoparticles, then they will provide you with better stability of these channels, and they will give you a higher thermal stability, better mechanical strength. Okay. So dimensional stability, that is why we can use some metal composite to make it more stable. If you have sol gel, so many the most popular or very effective method for preparation of these materials are sol gel process. You can have sol gel process is like you have a sol prepared and a gel, and then you mix them together and you have a coating and to get a stable kind of membrane. And if you have a layered composite structure, different layers of different functionality, or you can have reinforced like inorganic material decorated into a polymeric matrix. Some of the additives that are very popular is that metal oxide. Metal oxides, they improve stability, like they prevent the collapsing of water channels. Carbon based nanomaterials, they are having a different kind of objective or contribution, because they not only give you that carbon materials like graphene oxide or like carbon nanoanion, not only you can decorate the surface with different functional group, but also they can act as a bridge between different polymeric chains. So that's why at the same time they improve the conductivity, they also improve the mechanical strength. Okay. Fillers like metal phosphate or metallic fillers, they will be aiding in the transport. They can act as a transport enhancing agent. So that's why we tend to go into composite membranes. We have a lots of reports coming up in last 5 years on the composite membranes being used, and it is a very important research problems where many people are working on that to find an alternative to Nafion. Okay. So in that case, what are the different structures that you can expect? is that you can have ceramic particles embedded into a polymeric membrane like that. You can have thin film nanocomposite. So professor was telling in the previous slides that thin film, how the thin film structure we get. So that is actually a very good way to make this kind of membranes. Okay. So over ceramic support or over any stable support, we can have a coating of a conductive layer. That is one very good way to prepare this kind of membranes. Ceramic support over, so either way, either you can have a polymer as a support over that ceramic conducting material, or the other way also you can have. Okay. So they improve the ionic conductivity basically, and they minimize the electrical resistance. That means the gap between that green line and the purple line, if you remember, they get reduces, because that initial sharp drop we can enhance, we can reduce, and the slope of the line, that also we can reduce. Okay. Now that is about the main factor, like why we need composite. Now while we are doing composite, while we are choosing the membrane material, then we have to keep a few things in mind. Okay. First is that these are the different properties that we should be looking into while choosing or making a new material. They should have high ion exchange capacity, high IEC. How to do that? You can have more surface functional group exposed to your water channel. High IEC means that the ion exchange, the hopping mechanism that we have been talking about, that hopping or jumping of ions from one spot to another spot, that is enhanced by high EC. If you have low crossover, what is crossover? Crossover is like basically intermixing of anode and cathode gas. Okay. So you can imagine that our membrane purpose is to stop this intermixing. So the diffusivity of the gas through this membrane should be much minimized. Okay. Low fuel crossover. It should be stable thermally and timely manner, it should be stable. It should be highly conductive. They should have good mechanical strength, good water retention, otherwise this vehicle will not be useful. But one thing for widespread application, we have to have low cost or economical option. Otherwise, if the additive itself is very difficult to manufacture, then no industrialist will be interested to use that. Okay. So these are one of the key desirable properties of our membrane. Okay. Now here let us talk a little more about, so now we know about what are the functions that we should be keeping in mind to when we are optimizing a membrane. Now one of the things that I would like to discuss is the water management. Water management is very crucial in any kind of fuel cell, okay, because lack of water inside the membrane causes drying out of the membrane, and drying out leads to cracking and loss or lack of water molecules to do the vehicular transport. While flooding of the water will reduce the driving force for the diffusion or too much of water will reduce the driving force through the membrane. So what you can see here is that when we are having, let us say that when we are having any oxygen, so in anode or cathode where our water is produced, when we have a PEM fuel cell, we have water produced in cathode. Now in this case we have a negative concentration gradient towards this side. From cathode to anode we have a negative concentration gradient, and we know that whenever we have a negative concentration gradient, what comes in picture? Mass transport, right? So if we all recall our Fick's law, J equal to minus dc dz, right? All of us know that. So whenever we have a negative concentration gradient, our mass flux comes into picture. So when I have a negative concentration gradient in this direction, my water will try to go from cathode to anode side. And what do I want? What the direction I prefer? Because water is carrying the H plus. What direction I should prefer? H plus to be going from the opposite direction, anode and cathode, right. So, I have to stop this, okay, I have to minimize this, but in order to minimize this, I need to have lesser amount of water, that means that lesser amount of reaction. So, they are counteractive, okay. So, they are counteractive, we need a optimized level of water, okay, optimized level of water in my fuel cell. So, that is why it is very, very important to have a proper water management in a fuel cell, okay. Now, what are the things or the challenges that becomes? So, I told you that drying out leads to mechanical failure, lack of water to transport, flooding gives you a loss in the transport, loss in the driving force, so your transport also gets affected. So, we need a optimum level of water. Now, what is the challenge for us that we cannot maintain? What is why it is so difficult? Because there is electroosmotic drag, as I was telling, okay. Electroosmotic drag means that when I have a back diffusion, so electric transport is like this, when I have a back diffusion towards that side, so the water molecules, they drag the ions with them, okay. So, that is practically one of the challenge that we need to stop, and another one is that evaporation loss. So, water at whenever we are working at 60 or 80 degrees centigrade, some of the water gets evaporated and leads to non-uniformity, okay. And so, that is why how we can have a proper water management. Generally, what we do is that we have a humidifying chamber around the membrane in order to maintain a particular RH level. So, if you see the different conductivity of different kinds of protons at different RH level, with increase of RH, the proton conductivity generally goes down. So, we have to have a optimum RH level around 80 to 80% RH level that we should be maintaining for that, okay. We can have a hydrophilic coating, layer by layer assembly, hydrophilic coating should be at the top. Hydrophobic gas diffusion layer, so the gas we should pass out very quickly. So, that is why the hybrid membranes or the optimized flow design is very, very important for this kind of water management issue in a fuel cell. Okay. So, while we are choosing different membrane materials, water management is an issue, it is an operational activity we should be maintaining. But also one thing, while choosing particularly the membrane, which membrane you are going to use, for that important factor comes into picture is permeability and selectivity. Now, permeability and selectivity, I also told in the last class that they are counteractive. If you have more permeability, selectivity goes down. So, importance of permeability, selectivity, they have to have a balance between them. So, factors that affect this permeability is that if you have high membrane thickness, permeability goes down. If you have densely packed molecular structure of polymer, they do not have space to transport the ions. So, they are the crystallinity. High crystallinity reduces free volume. So, semi-crystalline nature of your polymer is preferable in this case. So, temperature and pressure effect, if there is strong gradient, then also we will have a loss of permeability in there. Okay. So, how do we do? What are the strategies for composite membrane that we do for this kind of membrane? We can use fluorinated polymer. Okay, fluorinated polymer, Naphthalene is a fluorinated polymer. So, that is why we have a very good conductivity of this material, but Naphthalene we can, if we impart it with even more conducting material that gives more selectivity, it will act better in that way. Okay, we can have cross linking to reduce the diffusion pathway. They should be straight channel. So, cross linking can be helpful in that case. We can have inorganic filler in order to channelize the transport procedure. We can have advanced layer by layer structure or nano coating with that. Then they will have a very good permeability, a balance between permeability and selectivity. Ionic conductivity is probably the single most important thing in a fuel cell. If there is ionic conductivity is low, everything else is not useful. Okay. So that's why the factors that affects ionic conductivity are the temperature. Higher temperature gives generally better ionic conductivity, but if provided there is no loss or collapsing of your ionic channel through them. So that's why microsegregation approach is very, very essential. Microsegregation approach is like proper structuring of your hydrophilic and hydrophobic region inside the membrane. Okay. So we have sulfonated polymer, perovskite and hybrid materials. Again, the stability of this material is also another point of material point you have to keep in mind, so that the thickness and the structure of the material you can have a stabilized environment into your system. Okay. So we can, in order to improve conductivity, different strategies which are being followed are nanostructuring, hydrophilic additive, cross-linking, doping with some rare earth material. Those things, they provide more ionic conductivity in this case. Okay. Now durability. Durability is one important thing, because in your case, if the membrane is not going long enough, so if they require frequent readjusting, then it is a problem for us. Okay. So chemical, the degradation can be of many types. Chemical degradation, like the environment, they are losing the mass. If there is mechanical degradation with the pressure, high pressure environment, if they are breaking, thermal with the temperature, if they are cracking, fuel crossover, these are the causes of membrane degradation. You can improve the membrane degradation by improving the reinforced composite membrane, protective coating, or changing the operating condition like that. Okay. So, but at the same time, you have to have how to know that your membrane is getting degraded. You first of all, you will first thing that you will notice is that loss in the ionic conductivity. You will also see increased fuel crossover, increasing rate of transport of gases. Operation lifespan effectively will be reduced to a great extent if we want to apply or adjust too much in the stability. Okay. So what are the like kind of strategies that we are employing for this kind of composite material making is that we are improving the stability, we are improving the interfacial junction distance, we are improving the water transport. So these are the main goal of making composites or choosing composites for different researchers all over the world. So they are also increasing the ion exchange capacities and catalyst, water dissociation through. So for these two, stability, ion exchange capacity, for that we can enhance by using materials effectively. You can use fabrication method effectively to enhance their interfacial junction or contact, you can reduce the contact resistance. You can increase the voltage and you can reduce the ohmic losses or increase the water transportation and ionic conductivity by changing the catalyst or asymmetric structure of the membrane. So if you have a particular membrane composite material, so if you want to develop or emphasize any one of particular property, now this will be helpful to know that which way you should proceed. If you want to increase the stability of your membrane, if you want to increase the water transport through the membrane, which way you should proceed. Okay. So what are the different manufacturing strategies that we use? Solution casting. We have seen a lot of videos about the solution casting in previous sessions. We also have extrusion. Extrusion is what? Extrusion is basically the hollow fiber kind of membrane. Okay. So you have a board liquid, you have another polymeric layer. We have seen video of that also, how to make a polymeric video. Electrospinning. We are applying electrospinning and hollow fiber fabrication is very, very similar, but in the electrospinning we are applying electric potential in order to reorient our molecules, okay, charged molecules, so that the structure of our membranes are very, very regular. And we have hot pressing and lamination, also phase inversion for those kind of membrane manufacturing techniques. We have seen more detailed explanation or videos in professors' lectures in other sessions. So we have nano engineered membrane, 3D printing enable 3D printing also to enable precise control. So these are some of the aspects that we can use for membrane manufacturing, like 3D printing is very popular nowadays, layer by layer assembly for that coating, extrusion, coating and hot pressing, they are some of the very commonly used or latest factor of this. Okay. One thing, while we are working on the composite membrane, one thing that is very common aspect is that of a new technology is the sustainability. So you should have a recyclable material. So for that your choice would be thermoplastic polymer or sulfonated aromatic polymer or hydrocarbon membranes. So any cellulose derived membrane is very much bioavailable, they are very much biodegradable, or chitosan, they are some of the components which are very much sustainable in nature. And you should also see that your fabrication method is not increasing your carbon footprint, so that entire process objective will be lost in that only. Okay. So you can have a nanomaterial integration. So yesterday we were having a very nice interaction or dissociation, that one type of membrane after use, after they lost their lifespan, you can expose them to a different type of membrane. So there are options like that, that you should be reusability of a membrane, you can have that kind of information in mind. Okay. So so for that, the options for your additive, I have summarized them into these pictures, that for improved performance, these are the natural additives that you can give there. Recycle waste additive will give you these properties. So cost wise they are having different materials. So these we also have to have keeping in mind that there should not be any health concerns by the leaching of the materials and etc. Okay. So for more industrial application of this kind of membrane, what we need is that we need advancement in the perfluorosulfonic acid membranes in the membrane material category. We need enhanced manufacturing technology in industry, which will be roll-to-roll processing for large-scale manufacturing, and we need to have AI and machine learning embedded into this case, so that they can control their own properties by the change, if there is any change in the surroundings. Sustainability and cost reduction is one more aspect that we should keep in mind for our enhanced market growth. So industrial application that they are currently in being explored or being expanded is that these fuel cells, I was telling you that home energy management, vehicle transport, even for portable laptop and smartphones, it is under research, it is not in market till now, that what PEM can be useful for portable research, etc. In military application also we have this kind of application. Some of the case studies. So I already told you about these two sectors in the automobile, Toyota Mirai and Hyundai Nexo for fuel cell vehicles. There is another case study by Bloom Energy where they used SOFC for stationary power generation. Okay. So they use this kind of ceramic material and they saw that there is significant reduction in their greenhouse gas. So they got good appreciation. Bloom Energy is an international power company. There is also another direct methanol fuel cell application by Toshiba. So they used it for military application. NASA is using alkaline fuel cell for their international space station, where our Sunita Williams is spent a lot of days there. So these are kind of their applications when we see for case studies for environmental for different applications. So for more impact on the environment, we should have a green process, recyclable material, bio-based material, sustainable fabrication process, and we should have a sustainability but not with a loss of functionality. So Indian government has got some policies and incentives for having more focus towards the national towards the green hydrogen or fuel cells. That these are the some policies that we have summarized here. So, so these are these are the whatever we had to talk about the fuel cells for hydrogen generation or membranes. Now the takeaway message for this is that we have to have all the aspects keeping in mind that they should all work simultaneously, so that not only these solar and wind that can be useful when they are worked together with these fuel cells and electrolyzers, they can be useful in all sectors of our life. And we have learned a few things, important aspects, that how to make it possible. So thank you all, and any questions? Thank you. Any questions? Yes.
I have 2-3 questions regarding this one. The very first one is, when we want to actually keep the hydrophobic and hydrophilic effects to the anode and anode respectively. My question is specifically towards this, that how one can determine the percentage or the weight of an hydrophobic material on the cathode side. I mean to say is that, if let us say that I want to apply the PTFE on the cathode side, then how one can actually estimate the amount of it?
So you want to know the amount of PTFE beforehand, before making them?
No, while making them.
While making them. So you want to know that you are making a cathode, so how much PTFE you should use?
Because
yes.
The reason to actually ask this question is that we have actually tried to, we made a very simple try to actually make a 1 PM fuel cell. So by that time I had this particular problem of an, generation of a little water vapor at the cathode side. So what usually that I'm understanding is this: there must be a problem of an, making the membrane a little bit weight on the cathode side, which should not be there basically.
Oh, it means water.
Yes.
Yes. Huh.
So I am actually in a haze of understanding that how should I actually avoid that particular thing. So if one can actually give the coating of a PVDF or PTFE on a cathode side of it, of a membrane, then that problem can be get resolved. But my question is this, that how one can determine that how much amount of a PTFE that is supposed to be applied on it?
Yes. So very good question, because one of the thing that we have with a hydrophobic or hydrophilic coating is that one probability is that the reaction loss, because if we have too much of coating thickness, we can use you can lose a lot of reaction efficiency. Okay. So one option will be to maintain, first of all, you should not have it in a moist environment. So your humidity should be totally controlled. Okay. Otherwise there will be accumulation of water vapor. One problem is that. Second is that it must be experimentally determined that how much of thickness of PTFE is causing you how much loss in the loss in your power generation output. Okay. So your activation energy, you should measure all that, that what is the reaction rate with a different thickness of PTFE. So only then you can have a coating of PTFE, or otherwise you should look for other options like a completely different cathode material for that, more of a less hydroscopic material, less of hydroscopic material. That can be other option for that. But if you want to determine the coating, I think it is very, very material specific.
I believe the multiple experimentation may give me the answer of this. Do you think so?
Yes.
Okay. The other question is actually also related with this. Now, you have answered me as well as that also, because I was again a question of an, if a membrane has to be actually applied, like GDL is there, gas diffusion layer is there, on which we give the catalyst layer. So the one that you have actually showed and mentioned earlier on a slide, where we make a slurry of it, and then the entire slurry is going to get coated on a carbon paper, which need to be get coupled or sandwiched with the membrane. So my question was again like this, that how one can again estimate the amount of an catalyst to be actually put it on the gas diffusion layer. But I think so, as you mentioned it correctly, that can
yes, too much of it can lead to agglomeration, non-uniformity in your matrix, and also too little of it will give you less efficiency. So you have to have a, I do not think there is a thumb rule applicable for all kind of material.
Because we, as of now, we are using in 20% platinum and carbon on it.
Okay.
Uh,
20%.
Yes.
So then your capex cost must be how much?
For a fuel cell right now, which the membrane size of an 5 centimeter square area that I have actually manufactured, it cost me somewhat around an 80,000 right now.
18,000. Okay.
Yes.
So it is a kind of a composite for you.
No,
Otherwise,
it's a simple PM with the polymer. That is I'm using an Nafion 212 membrane.
okay.
So being a mechanical that I can actually estimate the external part of it, I can actually reduce the cost over there.
Okay.
But I'm handicapped whenever I actually reach to the chemical part of it when
Okay.
it goes with the membrane and all.
Okay. I see.
Thank you very much, ma'am. That was a nice presentation and we really enjoyed it.
Thank you. Thank you so much. Thank you. Any other question? Okay. So thank you all. So we'll go
There
to
is a question, ma'am, from our online participant,
Yes.
Karthik D. Naveen.
Yes.
He wants to ask that what would be the best membrane for long-term usage of a fuel cell?
Different kinds of fuel cell will have a different material. Like say, if we are having PEM fuel cells, they generally, I was showing that they have a very long lifespan. But if you have operation at a very high temperature fluctuation or operation, then this operation lifespan will go down for that. So in order to enhance this lifespan efficiency, you can have reinforcement with some metal oxide that increases the lifespan efficiency of a composite. Yes.
And is there any feasibility and life scale study for various membranes?
Yes, there are a lot of reports already published. There are lots of reports. If you are interested, I can share a few publications with the participant. That will be useful.
Okay, ma'am. Thank you.
Okay. Thank you. So we'll go for next session. Thank you all.